I hope you all of them must have made some effort.
So we
Anyway,
tried, but
yeah.
solve we have some problem.
Yes,
How
yes,
to?
yes. Okay.
Yeah.
Actually, I'm going to start with that and try to explain, and additional details will be provided for you, so that when it is next time when you come across such problems, you can work it out easily. But I have introduced a lot of errors into the problem of this, whatever which I have sent, and make sure that you people are really looking into that and then making the corrections. So now I have all of them are corrected, and additional inputs will be available for you to learn. And then you can proceed further to the learning the Mathematica code, which we have started the Friday's class, last Friday class. Okay, we will start from here. I hope that there must be some effort from people. I do not know how many of them could get this angle pi. What could be the possible answer? Anybody could get the angle pi? See, find the position at which two paths intersect, which means if you know the pi, you can fix the position now. What is the position at which they meet? Okay, there are two asteroids. They follow a particular path that has been given here. Anyway, we'll just start look into this, and then so this is already I have plotted as a parametric plot in the previous class itself, and I've shown the result. Okay, then this is another plot for the next problem, next part of the asteroid where 1414. This is 1518. 1414, 1414. This here it is 151818. Now they are going to meet somewhere along the path. That path should be identified by solving this equation, which means I have to equate these two equations and solve for the pi, find out where do they meet. Okay. So look at this plot also you have seen. They are meeting at this point. Okay. And there will be certain angle between them. It is something like a two planes are there, they are passing through each other. Okay. If you look in terms of three-dimensional picture, there are planes, they are cutting each other, and their meeting point is these two. And they make particular angle now, that angle can be found. Okay, that is what your pi. As I said, this can be made as a polar plot, which you have seen, and polar plot simultaneously you can put both the asteroid parts here. You can see both of them have been put here, not like what we have done here. We have made independently and we have put together. Here it's both together and the meeting points are same. Okay, and what you have to do to equate this first part of this equation to the second one. You see, I'm equating this A1 1 plus of epsilon cos pi equal to A2 1 plus of epsilon 2 cos pi. Okay, I've assigned this A1, A2 for the number what he has given as a 15 and what is it? 14 and 15. This is A1, this is A2. So this is A1 and A2 that has been assigned, and epsilon 1 by epsilon 1 cos pi. They're, at this point they are meeting, which means their magnitude must be equal. That's what it means. Okay. So now solve for the pi. I'm getting this number. Arc cos of this and arc cos of this, there are two possible roots, and then there is a multiple roots also possible. This number is nothing but your 2 pi, and ci can be some integer, it can repeat again and again. 2 pi I repeat, same thing you get back again. Okay, so now arc cos, substitute this A1, A2, epsilon 1, epsilon 2, which is given in the problem. I'm putting as a rule and then substituting to this arc cos, and then you can see this is I copied and pasted here. Positive root I have taken, you can take a negative root also, doesn't matter. And then this has been converted into degrees instead of a radians. Okay, I hope it's clear for all of you. Is it right? Let's assume that you are having a clear picture about it. Then substitute A1, A2, epsilon 1 and epsilon 2 that are available, and substitute, and then look for the result. It is happens to be 120 degrees, the angle between them. This 2 pi is the number which is 6.2819 that is sitting here. Okay, this has a, since it's a periodic thing, it has a multiple roots that are possible. So whatever is available, if you repeat again to this 2 pi times, you will get back the same situation and you will get this. That's what it means, going around and around. Whether it is a first loop or a second loop or nth loop, you have the same they are going to meet. That's what it means. I hope this is clear for all of you. Fine, now I can proceed to the next one.
Yes, sir, can you show a simple example how I have a straight line and a parabola,
Okay.
and they are meeting at 2 points.
Okay.
Uh,
I'll show you that. I'll show you that.
yeah, okay, sir.
It's possible. Parabola, I can have a line passing through that, find out the roads. It's possible to find the roads. It's something like a system of equation you are solving. Okay, this is again n-solve numerical. I'm solving. There is a 2 equations. No, see, you can look at the visually. You'll feel it. No, they're meeting. No.
Yeah. 2 places they are meeting.
What does it mean? This and this magnitude must be equal. Otherwise, they don't meet. Is it not? Magnitude of this and must be same as magnitude of this, not this point.
Right.
So that's easy to understand. It's not a difficult thing to, because I'm equating them, which means they are at this point, meeting point where particular value of pi, this magnitude is equal to that magnitude. Therefore, that point happens to be 120 degree because I converted the radians into degrees to show it in the form of a theta, okay, which is in degree. So it's nothing great here. Like a 2 lines are cutting each other, no, meeting point is going to be solution. And we have already seen slope becomes 0 means they are going to, the slope when you plot it, it's going to cut the axis. Cut the x-axis, then only it becomes 0. Similar situation, 0 happens to be other places where when this magnitude equal to this magnitude, you will get this solution. Okay, that is what the solution which I have found. And I substituted back because 1 line I have made it. This, instead of finding this and making a substitution, pi is the one which is solved and I am getting it back, and that is substituted. I am getting this equation as a solution. Get it now? For example, one more time I'll repeat x, right? Note to you, solve a x square. This is a quadratic equation plus, which we have already seen, bx plus c equal to 0, solve for x, and you see, solve solution x will be found, and that will be used back again and substituted for the x. So if I take out this, I find this root here. There is a rule substitution. Okay, x first root, second root. That I am going to make it here, x substitute here. You see, I am getting it directly the value of x in the list, first root and second root. That's what I have done it here. Nothing great here. Instead of making one more step, I have done it within the steps, within the same line. It has been done. Here is the same thing. Pi is be found. For example, if I take out this, let me take out that. I remove it. You see, I'm getting this as a rule. Pi 1, pi 2. I don't want that to be again another line. So I just add this, substituted, and that has been removed. That arrow has been removed, and I'm getting a solution 1 and solution 2. I've taken the positive solution, copied here, and then use it. If I define it, that can also be defined variable, can be taken. For a clarity purpose, I just copied and pasted over this alone. You follow? I'm just taking this alone. Okay, copy and paste over. Substitute this A1, A2, A3 and multiply by 180 by pi. I'm getting 120 degrees. That's what the result that what we need. It's like what has been done here. We have done it. You get the point now. You see how interesting now you are able to substitute. Found x and make a rule form. It is appearing that is being substituted. I'm getting the value of x automatically. First root and second root. So exactly same thing has been done. Okay, you are able to see that, and polar plot some more details which you have seen in the previous class. So this is what the solution to this problem. I hope this is clear for all of you. Nothing great if you start practicing it and thinking it over the equation and the solutions. See, visually also we are able to feel, yes, they are going to have a same magnitude at this point. And it is equivalent to having an orbit. They are passing each other with an angle of 180 to 120 degree. They have to meet somewhere. Okay, 2 different planes, the 2 different circular planes, they are crossing each other. The crossing point is this. Okay, this can be shown. Probably I can spend some time and show it on the 3-dimensional also, that planes crossing each other. with an angle of 120 degrees. Okay? I hope it's
Yes,
clear
sir.
for all of you. Go to the next problem. How many of them made an effort to solve this problem? Basketball is launched from midcourt at an angle of 30 degree angle, at a 30-degree angle with a horizontal, and then at a height 2 meters towards the basket, 12.5 meters away. Height is given and towards the basket, which is 12.5 meter away. If the rim is 3 meter above the floor, neglecting air resistance, what must be the initial speed of the ball in order to sink the basket? So how do you approach this? Some idea you have?
It's like a projectile motion,
It is a projectile
with
motion, but you have to think little more carefully about the problem. That's all. Equations, whatever which you have seen are same. Okay, horizontal and vertical motions. Only thing that inputting should be done properly by understanding this issue. What happened? This is the height 2 meters are already been given. This is for the vertical. And where does it in this is initial height. This is going to be the final height, is it not? A person who is whose height is somewhere about 2 meters, and the basket is in front of him, which is about 12.5 meters away from him, and which is at a height of 3 meters, which is the final height. Okay, for a vertical motion, this is the initial height, then this is the final height, and the angle is given, and the range is also given 12.5. Okay, now you have to solve that equation horizontally and vertically, and see that what is the initial velocity with which it should be projected so that it can go to the into the basket, sink the basket. Okay. See, you have to make some effort computationally. You have to think and get an idea about what is the equation that you have to use, what are the parameters that are given, and if they are with that parameter, what I supposed to that you have to think. Then when you are thinking, you will get an idea, yes, this is what all are given. These are all unknown. Two equations are there. Is it possible to manipulate one equation to another equation so that I can get the parameter in the form of whatever is given in the problem? Those things, when I substitute what I need, can I get it? This kind of a thinking is required. Okay, Mathematica will not solve the ideas. It will not be okay. It will not give an idea for you to think about this problem, but it will help you to solve the numerically easily, and also you can visually feel it. Yes, what I did is right like this. You are going to see the same thing here now. Visually also one can make it, because I wanted to show you visually also, so that you will feel, yes, how equation one can manipulate, handle and understand. Okay, so this problem, can I make it visually? Solve the problem, find out V0, and try to look at the same equation after substituting back. And if I make a plot between the parameters what is available, and we make a plot x versus y, and see whether the numbers what you have calculated, you are getting it absolutely without any ambiguity. And you make sure that what I have done is right, 100% right. Whether you don't even know about the answer also. Forget about your answer. But your approach is right, your answer is correct. You will, if you are confident, then you refer your answer, you must be right. Okay, that is what the confidence that you should have. So let's start from this equation. You know, x is real, this is the V0, cos theta V0, which you are interested to find. T is not available, no information about the T. Y0 is given as 2 meters. Do you agree with me?
Yes, sir.
Right. And what is the final height? That's going to be 3. Correct?
Yes, sir.
You have to think about this. Then again, you have a V0 sin theta, which is your vertical velocity, this is horizontal velocity, and half gt square, of course, we know. G is substitution. Now, in this equation, two unknowns are there. It's a V0 and time also we do not know. Time is a varying factor. But what I can do, if I manipulate this equation carefully, find the t, if I substitute it, I'll get in terms of x and y. Is that right? I'm finding from this equation t, substitute that equation, I'll eliminate the t from this equation. Then I find X is available, Y is available, V0 is not known. Then if I solve that V0, I can get it. Are you able to follow the steps what I'm suggesting now? What I'm suggesting is find T from this equation, substitute T here. I'm eliminating the T from both the equations. And then this will be in terms of Y and X. Y0 I already know. Y is also known. X is also known to me because that is the range which is covered with that velocity, 12.5 meters. That can be substituted. Is that clear for all of you?
Yes, sir.
Okay, now you can proceed. See, this picture you should get it to start with. Then only you can proceed with the Mathematica, what you want to do. Okay? Correct? Right. We'll solve this. Take the first, there's nothing to solve here. You can write equation T equal to x divided by V0 cos theta. That's what I'm getting. Which is 1 by cos theta is secant theta. I have this equation. Okay? And I'm substituting back to this equation, the second equation, in which I know the initial height y0, which is equal to 2 meters, that is substituted. T already I found substituted. I'm getting this equation in terms of x and theta because theta is already given for me. Now you see, everything is known to me except V0. Is that right? X is known, theta is known. V0 is the equation which I am supposed to solve. So now I know this, I'll take this equation, substitute that as this height is can be taken as maximum height is 3, equal to 3. Okay? I'm using this equation, which is the vertical component that has a value 3 that is given in the problem that has been used here. This is the initial height, this is the final height, this is the equation which has been converted by eliminating T in this form. Now I know all the parameters except the V0, which is disappearing as a V0 square. There will be 2 possible roots and I can take a positive velocity. That doesn't matter for me. Okay, a negative also it is going down instead of going up, it's going down. So it doesn't matter for me. So you take a V0 positive now in this case. Okay. So my V0 is 12.8 meters per second by solving this numerically. Sure? You can check it now. I have not done any checking, but I am sure my answer must be right because I will cross-check that answer by using certain things. For example, I know now V0 because after solving that I found it. And then know the final this thing, height also, because final height has already been given. I substitute that V0 here and get 2 possible time scales that are appearing as a root, which is an additional thing which you are doing. The problem only asked up to find out this. I'm trying to do this, substituting back 2 time scales at which they are going to move, which means final time at this point, it should reach a distance of 12.5 meters. That's what it means. Okay. Initial time, it seems there somewhere. It also seems to be available. This time is also because 2 roots are there for this equation. Okay. Here also 2 roots, but it makes sense only taking a positive. Here you have a 2 roots are which are available. Now you see what I'm going to play here. I have the horizontal component, vertical component. Unknown was velocity, which I have found, and I'm going to substitute it back. And to solve this problem, I found how long it is going to be what is the flight time, how much time it is going to be in the air before touching the basket. That is 1.12581. And it reaches this height twice. That's what it means. 3 meter height has been reached by this is twice. Okay, let's see this. Okay, I can plot this against this until the time ends somewhere about 1.13 seconds. I've taken this 1.13 seconds is here. And I am putting the path, another list of plot to show that it is actually like a ball, it is moving, like a basketball, it's moving with the red dots. Okay, same picture again. but put it in the list plot as a point which is moving on the path. Same thing you can see, I'm repeated here. Only thing we made a list plot. The list will be followed in the form of a red. This is some blue line. Okay, this is a parametric plot. This is the list which I have created for that by evaluating the x component and y component, and that list can be again plotted following the curve. The trajectory for both of them are same, but I made one of them is a dot-like structure, and another one is a continuous line. And if I make a manipulate and show together, it appears that as if that they are visually seeing the something like pushing the basketball from particular velocity which we have calculated and found. And you can see here now, okay, I'll show you by, it is something like it started at a meter of 2 meter height and supposed to reach 12.5 meters with the range, the height of 3. That should happen. Then your problem is right. Check. It's going to happen. Is it happening now? That's fine. So you can see. So you don't have any doubt about this problem. I'm 100% sure that this is working. This problem is right. You see, the height reaches higher values also, but at the end, no, it is only 3 meters when it touches the basket. There are 2 time scales at which is crossing 3 meter height. One time scale here, another time scale is here. That's what the 2 rules. 0.1809 second it meters. The time is not seen here because this is x range, this is y. The time is not seen explicitly because you are plotting as a what? X versus y for a different time. And at the time of 0.18109 second, it touches the 3 meter height. And again, it touches the height at 12 point. You can find out the range at that point. If you wanted to check how what is this time is right or wrong, you can check what is the range at the time of 0.18109 by using this x value. You can do it. You can do all those things and confirm yourself. Yes, it goes to 2 different time scales with the same height. I can find out through the range calculation. Can be found. So this is 12.5 range. You can see the dynamics how interestingly happening now. Somebody is pushing the ball, and there are distance are given, time is getting connected to these forces are involved. Okay, very nice problem to understand. And this is how one should get a clear-cut understanding about the given problem. And if you are sure about this, you know whatever the way the problem has been given, you will really in the position to tackle that problem. That is a very, very, the idea here is to that whatever the form, see, we should understand how this has formed as basic equation. And the problems can be asked in any form connected to this problem. It will be only a manipulation of these equations. For that, such in manipulation, this is helping you. And then there are things which is very difficult to rather to imagine, but we are able to feel that whatever we have done is 100% sure, no ambiguity at all. Should we have to check the textbook to know the answer? No, not necessary at all. They are sure. You have much more information than what is the
Yeah, it is visually
much more information is available than what is the textbook is expected to ask. They ask to find out what is the velocity, but it is, we are sure every parameter that has been connected here, we are able to get the result. This is how, this is additional information which is really required for you to get a deeper understanding about the given problem. Okay. If you work it out like this 2-3 problems, then given to this various forms, sometimes they ask time factor, that they will ask velocity, sometimes angle they will ask, doesn't matter. This problem, sometimes they may ask range they will ask, or height, what height it reaches. Okay. At a given time, what is the height of the object? Doesn't matter for us because every information is available with the equation. It's a question of how we are going to manipulate that. That's all. That's the point we wanted to emphasize here now. Velocity is asked here, but sometimes they may ask range, other parameter will be given. Sometimes all parameter will be theta they will be asking. Doesn't matter for us because all are interlinked, and it is question of how you are going to manipulate this equation to get the results. And you should know minimum Mathematica codes. That's all. So what are the codes which you have used now? One is solve and n-solve manipulation, and there are show. There are other parametric plot, list plot. These are the things which is routinely we are going to do for every problem again and again. Okay, therefore it is a really wonderful tool for us to get a deeper understanding of a given problem. We should not miss what we needed. Okay, see what is important is understanding the base. That understanding of the base becomes much deeper when you try to do like this. That also happens. But this Mathematica will not help you to understand the base problem. Base problem will become deeper and deeper and understand much better when you have a clear-cut picture of what you want to do with this equation with the help of the Mathematica code. That will be clear to you. Any given problem, this kind of an approach is really required for you. If you follow them, then you are sure about the problem. And as I said, any form, let them ask connected to this problem. Okay, projectile motion, any form of the problem, you can tackle it. This is what I wanted to say. You take any, without any inhibition, without any hesitation, you can start work on the problem. Question of sending some extra few minutes, that's all. Okay, so that's what the point which I wanted to bring it to your knowledge. Okay. Fine. Go to the next problem.
Yes, sir.
Any clarification by any students? Students should ask some clarification or doubts, this, that, they should ask. Okay. Right. Go to the next problem. See, I'm giving a problem to exercise previous class. At least you go through that and what is to be done for that, you should have a base. Then I explained now. And then in future, now you try to look at similar kind of a problem, try to work it out to start with. Then alternate problems that are available based on these equations, then work it out on yourself. And then make sure this kind of an understanding that you are getting. But this visual picture, any questions, any form they ask, we can always make it. Suppose angular projection is varied. Okay, same problem. If I make an angular projection 45 degrees, the whole thing will change. Okay. If I make a 40 degree, the whole problem will be getting converted into another form. Range will change. You can give a problem to estimate with all the other parameters, find out corresponding things to happen, what could be the angular projection. It's possible. Okay. And you can find out time related problems also. After obtaining, you can find out what are the stages covered at different time scales and maximum take. This is the maximum range, but maximum height, we have not come to the maximum height in between the flight. Maximum height is somewhere here, it is much higher than this one. Is it not? So maximum height reached by this is much higher than the height because we are projecting as a projectile and we wanted to drop it inside that. This will be the easiest way to do it with the forces that are involved. That's what it means. Okay, now this is 30-degree angle. You can put all those information into the picture also. So put an arrow mark here, and the angle can be shown as 30 degrees. In between, every time when the red dot comes, what is the time, what is the height, what is the range, all can be even pictorial form, you can bring it. You have to spend some time to put all these things in this. Possible to do that. Okay. These are the things which I will do. That's what I said, you should try to understand. But the content errors, correct them, present the results neatly, put as much information as possible for a given problem. Don't restrict to the problem whatever he has asked for. Proceed further, extract as much information as possible, and connect them to the other problems which you have already learned connected to this kind of a problem. Okay. So now let us go to the other problem now. This is some more interesting problem. This gives lot of learning if you spend your time systematically, and for an MSc you can have a nice 3 to 4 months project. Excellent project can be done. I'll show you something which is connected to all of them. Somebody is interested, they can do an excellent mathematical problem and you can write a small dissertation. It will be extremely useful for understanding the dynamics that are happening in the circuits. This is actual dynamics going on. Charges are there, they are having a dynamics now. Okay, they charging and discharging, then inductor something happens, resistance something happens, and capacitor. And this is in parallel. If it is series, two elements are there, what happened? Three elements are there. It is put in series here and it's put in parallel. And there are many things that one can learn. Okay, let's first look into the problem and get an answer, and then see what are the additional things that one can make an effort to learn. Okay, let's start read the problem now. So the figure below shows a resistor and an inductor and a capacitor C connected in parallel. And in the previous class, I have shown if you RC alone, you have what is the result. Now let's try to work it out RLC itself as a whole. Now, an AC potential difference V of t, which is equal to V0 cos omega t, which is equal to real part of E power I omega t, is applied across the open terminal C, which means you are applying a voltage, AC voltage across this. I think you follow the mouse arrow here. This is what your potential difference applied across the open terminal. This is open terminal. And you are going to, these are all the wires connected. This is also wire which is connected. This is inductor form. It has been filed. File is there in the inductor form. And this is the simple resistor. Has a finite value. This has a finite value of inductance. Finite value is the capacitance. These are all connecting wires. And they also has a resistance. Please remember. But the magnitude may be very small. But with the AC, you should be very careful about using those wires. Okay, one should take care of that. Okay, we call it as impedance matching, and then we assume for these problems, this resistance, additional connecting lead resistance are taken to be, there's no resistance contributed to this, contributed to this. Okay, assumptions. Okay, now in this case, the concept of resistance for DC circuits can be replaced by impedance for AC circuits. So you have a resistance. If I have a DC source put across this, replace this source by a finite value, say 5 volts or a 10 volts DC across it. That is, now here it is been DC circuit. It is replaced by an AC. When you have an AC, you don't call it as a resistance, we call it as an impedance for an AC circuit, because phase automatically enters through this capacitance and through the inductance. 90-degree phase of resistance is sitting here. This is 90 degree, this is 90 degree with respect to the current and the voltage. So therefore, you have please note that 1 by omega C is ohm unit. Similarly, Z suffix L, which is equal to I omega L. Omega L is also ohm, or also in ohm. So this will be reactance, which is equivalent to that 1 by of I omega C. This is the reactance. This is the reactance of the inductor. The Zs can be used as a resistor using the same results for DC circuits. I already mentioned that. But the complex results has both magnitude and a phase, as defined by the absolute value ABS in Mathematica, and phase, the RG, argument, the phase. Now, find an expression of the impedance Z of the circuit segment in terms of RLC and the frequency omega. Using the realistic circuit values, 1 kilo ohm, 100 micrometer farad, L equal to 5 millihenry, plot the magnitude and the phase of Z as a function of omega. It's best to make the plot using a log scale for omega. See the function log linear plot, which will do this for you. This is again Mathematica code informations. You can read them. And suppose now solve the value of omega, which the phase passes through 0 value. Right? So one should use the solve. How we are going to solve the complex equation? That's what going to be a challenge here. You understand now? You have a previous problem solved is all the real quantities, but here is going to be a complex quantity. How do you handle this problem? He has given some input for you. You will follow them. They will follow other easy methods also. Following this, whatever he is given, not so difficult as he is given. He mentioned something, it is tough job to, all such things can be found easily. Okay, now let's see what is the problem that has been given. Problem, what are the input or the values that are given. This is the resistance. This is your capacitance. I have asked for numerical value, of course. If you put a decimal, you don't have to add this numerical, which I can remove it as well. Remove it, put it as 100 dot. Okay, 100 or 1 point. So we'll make it as the decimal form. This is 5.0. Because already they are having 10 power minuses. Okay, the numbers also converted. The value of resistance is the first one. Capacitance, second one. Third one is the inductance. You know, this circuit has a resonance. I think all of them are familiar with the resonance. In the circuit, LCR circuit has a resonance point. That's because you have an LC, so there's going to be a resonance. That resonance point we can identify and locate. Okay, that is known to us in terms of the LNC. Omega is equal to 1 by square root of LC. Okay, so this is the resonance points. What do you mean by resonance here? So we don't like RC, we see broad this thing, but here it's going to be a particular point in which you have the so-called the resonance point that can be located. This will be 10 power 6, 1.4 and 4, 10 power 6 radians per second. Okay, that's what the resonance here. Now we have to find out what is the impedance, like what we do in the circuits that already I mentioned is 1 by R1 plus 1 by suppose you take it as R1, R2, R3. This 1 by R1 is this. 1 by R2 is this I omega L, that 1 by I omega L. Here it is 1 by I omega C. That has been taken here. See 1 by R, 1 by I omega C, 1 by I omega L. That's going to be effective resistance, which we call it as an impedance now. 1 by F complex, R is the complex impedance because it has a real part and an imaginary part. Imaginary part has the two components which are having a capacitive and inductive type. This is what your equation, which is found by using a Kirchhoff's law. Apply the Kirchhoff's law, you can get this one. Okay, so that's what your equivalent circuit, the effective resistance rule that has been followed here. Now, I have to take the RE. RE is inverse of this. Take an inverse on this side, take an inverse on this. You can see complex expand, find out the absolute value of this that has been found. ABS is nothing but your absolute value. Is it okay? Complex expand. See the inverse quantity here. This should be, the whole thing should be inverted back. So that we'll get a, this is 1 by of R effective is 1 by of Z of omega, and this is your admittance. 1 by of resistance is the conductance. In a complex form, we call it as an admittance. So this is what your impedance now. I have taken the inverse of that impedance has been found. Find out what is the ABS value. This is what your ABS value. That's what he is asked to plot. Plot the, where is the problem? Complex result is defined by this, is that magnitude. Plot the magnitude and phase. This is the magnitude of, okay, this is the magnitude for the circuit. And we have already know for a given RC circuit, there is always a quantity called resonance point that's equal to 1 by square root of LC, which means you would get the either current or a voltage has a maximum value at a given frequency with the other component elements L and C. At this point, you see, you'll get a resistance. Okay, I substitute that, simplify, define the resistance. When the resistance is minimum, you get a maximum current. That's what it means. Okay, this is sort of a reference point at which I find there is going to be a maximum value of the current that is possible. If I increase the resistance further, then you see there's going to be a shift correspondingly. Okay, so now this is what the point which we are interested to locate, and then try to understand what is happening with respect to the variation of L and C and R on the plot with respect to the variation of this parameter, and also peak position, what is going to happen. So let's not worry about this part. Refine is the suggestion that he has given for solving it. Let's not worry about this part. We'll learn about this afterwards. Argument already we have mentioned it, but we'll again go through this. Complex expand, find out the argument of this complex quantity. This is a complex quantity. I want to know what is the argument, which is the theta which you are interested. Argument is nothing but the theta, which means cos theta, sin theta divided by cos theta values. You can see the complex argument, cos of this argument, sin of this argument. That's what it means. Okay, you find out the absolute values and then take a sine and divided by cos, which is going to be arc tan. That is what automatically evaluated by this. If all the numbers are given, calculate, give the arc tan. Okay. Alternate way to look at it is take the imaginary part of the complex quantity, divide by real part. What do I get is the tan phi. Tan phi, once you know, phi equal to arc tan of that. That is also another way to look at it. Both are the same. Either you can try argument through this evaluation. Directly you can take an argument, feed all the parameters, numerically you can evaluate and give the result. Or find out the real part and imaginary part, take a ratio between imaginary. That's what actually means. You can see this arc tan of this and this. That is what I am doing it here. Taking a ratio. This is arc tan of x comma y. Okay, that's y by x is going to be arc tan. That's what precisely I am trying to show here explicitly. This is the imaginary part. This is the real part. Take a ratio. That's going to be where tan phi. Take an arc tan. That is what the result is given by using the ARG. Okay, I think it's clear for all of you.
Yes, sir.
Please go through them carefully and then look at it. Now you can see the cos here, sin here, then arc tan. I am trying to find out the imaginary divided by real. This is going to be tan phi, and phi equal to arc tan of this. So I plot this and this, I should get one and the same for a given parameter. Okay, let us look at the first part of it, plot the magnitude. Okay, I'm going to plot the magnitude for a given parameter. For the first R value 10 power 3, C is 10 power 10, that's also given. And I have L, which is 5 millihenry. Okay, so we have found the omega resonant point is 1.41 421 into 10 power 6. That should be observed first if everything goes well. So now I have taken this ABS value directly. Look at the log linear part. What does it mean? Log linear part means this is log and this is linear. This is linear scale, this is the log scale. You can see this omega radians per second starts from 10 power 3 to has gone up to 10 power 10. See? But 10 power 2 to 10 power 10 is plotted. This is 10 power 2 to 10 power 10, that is the range. And how many orders? 8 orders of magnitude of scale variation, in which value response is seen. And this is your modulus of Z omega. At the peak, okay, resonance point, I'll get a resistance. That is what the result which we have already shown. You can see here, substitute omega equal to square root of 1 by RC. I am getting the value of R. That should be available there. This available as 1 kilo. Is that right? Graph has that information. And I have to locate what is this resonance frequency. maybe you can find out that by get the coordinates somewhere about, get the coordinates somewhere about 1.14 something. We're going, is it not? 1.4 10 power 6, no?
Yes, sir.
So around that, you have a peak position. That information. So which means resonant point has been located. At the resonance, what you get is the resistance. Okay. Which means this at the resonance point, resistance equal to the 1 by of omega, that omega c, and then L omega. All the three are equal in magnitude. That's what it means. Okay. These are the values of C parameters. Right. Okay, so let's see what is happening now. I think I have put a capital letter again. That should be converted to C because already this variable is available in Mathematica. It's a Mathematica reserved letter C. See, red ones are showing na capital C. The reason is very simple. You look at it. Double question mark. If I put C, there is already C. It is reserved for Mathematica code. That is why it shows as a red. Hello? C is by default, it's meant for some other purpose. Which is
Velocity of light or?
No, C is not velocity of light. This is meant for when you solve the differential equation, you have a constant, no?
Okay. Constant of integration.
Constant of integration, constant of solving the differential equation. So C, I, 1, 2, 3, like that, it goes on. Therefore, that is reserved for mathematical code. And when I use this capital letter, it gives a indication that be careful that you are using already defined mathematical code. Make sure that you are not clashing with that. That's what it means. So I just take out that and put it as a small c. So that will not be an issue at all. So we'll first do that one and then try to find out each one of them by executing one by one. So this is the parameter given. And you say LCR circuit, immediate thing should come to your mind is there is going to be definitely a resonance point that should be evaluated for a given value. Done. Now this is your effective impedance. And I am going to find out ABS value that also has been found with a small c now. Automatically convert. Then this I will make it as a small c. This will also be converted as a small c. So avoid the clashing of the variables with the mathematical code. Okay, now I am simplifying it. Omega equal to 1 by square root of LC. That's the magnitude is R. So this is for some other purpose. Let's not worry about that. What is the argument? Argument again, I will make it as a small c here and convert it into complex expand. I'm getting the result cos and sine. Here again, do that. The small c, convert them. Okay, so this is done again. Complex expand, take the ratio between the imaginary, the real part. Okay, so fine. Now we are going to plot log linear plot of this and manipulate for other values. You can see that I'm going to cover the range of 10 power 3 to 10 power 4, 5 to 10 power 4. This is about 2 orders. This is about 4 orders inductance. And when you are using this manipulate, you can see here, this is bigger when compared. This is greater than this one. Am I right? 10 power minus 10 is greater than 10 power minus 12. Is that right? Similarly, here it is smaller to bigger. This is greater than this one, whereas here it is the other way around. And here again, this is smaller to bigger. When you are using manipulate within these arguments, there is no issue at all, whether you are going to give a smaller value first and bigger value first. That doesn't matter. But when you are making a plot, any plot, this first variable must be lower value and this must be the higher value. Otherwise, plot will not be seen. Won't be calculated. You can cross-check it, any given graph, any plot that can be checked. But manipulations can be done in any way. It can from smaller to higher or higher to small. That's not a problem. Please remember that. So this order should be maintained. The initial value must be smaller than the end value. Otherwise, it will not be, graph will not be appearing. If you want to check it, you can check it. Now I am just putting 12, 10. So something has come which is absolutely nonsense. It is not correct at all. So now you try to avoid that and make sure that you are having a proper range. Maybe log plots might be working out. I want to check plot x, okay, varying from, let me take x from 3 to 1. Plot. It's coming, no problem. So the earlier version I have this problem of this should be taken properly, otherwise I used to have a problem. Now it's fine. It can be small and bigger also, doesn't matter. We're under the impression that is still followed. No. 22 doesn't matter. Okay, that issue is not there, so you don't have to worry about that. That's been eliminated. The earlier version should be given properly, otherwise it cannot be given the plot. Okay, now it's 10 power 2 to 10 power 10, which is plotted, and other things have also been given. And we are using the control placement at the top of it so that we can see the variation here. Now, what would you expect when you change the R, when you change the C, when you change the L? L and C, what it does? It changes your, this is what? What is this one? If I change L and S, omega R will be inversely proportional to L, inversely proportional to C with the square root. Will that happen? It should happen. Otherwise, the equation is wrong. So now I am increasing the L. What is L is increasing? Yes. When I increase the L, this peak will be should shifted towards the left or right?
Left.
Move towards the left. It's moving. It's moving. It's moving. Similarly, if I change the C, so you can see the consequence of shifting this C. And if I change R, R is going up. You see, it becomes sharper and sharper. Resistance becomes sharper and sharper. But if you look at the current will go down because its impedance becomes very large. So now you can see these are the something. The R doesn't have any influence on the peak, but it has an influence on the width. Full width half maximum. That's an influence. So RC circuit, you can manipulate your full width half maximum, which means if you call them as a band gap, allowed values of the AC signal, that band gap can be controlled. Is it not? And variation of this with respect to R, again, that's the same thing going to happen. Similarly, C. C should also get shifted down. You can see. Okay, so width can be controlled by changing the values of L and C plus, because RC is going to be the bandwidth of this. This information all can be studied when you have a LCR circuit. So now what are the other things one can do? How does this influence your bandwidth? Shifting the frequency. Shifting the frequency. Okay, this is shift in the frequency. All this that can be done can be used. Because when you change the C and L, please remember that its variation may not be too big because it's 1 by square root of L and C omega, is it not? So therefore, it may not be shifting too much, but there's going to be an influence on that, increase and decrease. I think capacitance I'm just reducing and increasing the index. That's why you have seen the other way around. You remember that? See, when I change this, it's going other side, no? You might be wondering how come this is happening. Because you are going from bigger to smaller. That's why it's going other side. You follow? If somebody might not notice, somebody is asking that. I'm going from bigger to smaller. That's why it's going other side. Getting it? Please
Sir, can you explain it once more?
With this C influence, okay, I'll start from smaller well. So that inverse relation can be understandable. See, I'll go to from smaller to bigger I'm going. So that now you can see when I change the capacitance also, it will be shifting. See, it is smaller now, it's shifted. Now if I change, see what happens, you see. Previously what happened? It was going to the right, no? Now look at the, see, it is inverse relation, it should get shifting towards left, both variation. It should happen. Is it happening? Am I right?
Yes, sir.
It is right now, because previously what I did is, this is small, bigger and smaller. Now it is,
Okay, sir. Got it.
Ah.
Okay.
but I wonder that, something is wrong with the equation. No, nothing wrong with the equation. It is a parameter which we have not taken properly. Smaller to bigger, whatever you do, increase the capacitance. Shift will be there toward the left all the time because inverse relation. Find it? The peak position already shifted. You can see this peak will be somewhere here right now. And then if I shift it now, the peak will be peak shifting. Are you able to see? Is it shifting now? You can see there is a shift here.
Yes, sir.
This has an influence, and the broadening takes place. And your RC is going to be your bandwidth. Okay, so this information can also be studied. Now, this is with respect to LCR, which is in parallel. I wanted to send you some materials for you people, whoever is interested. You can take interest to see that this problem can be studied in detail. I'll just show you this. See, this is actually meant for electrical engineering, but physics people, we know that we will be using very often this electric circuit analysis. Okay, LCR circuit, series, quality factor, and then bandwidth, half power frequencies. They are very much useful in many number of places. Okay, resonance in parallel. Parallel RC circuit, thanks. This is what which we have seen. Dynamic impedance or a dynamic resistance. You see, you know, induction heater. This is the idea here. Match with the resonance. And there's going to be enormous heat, the highest temperature that can be achieved by using the induction heater. This is by resonance. Look at the next. Various domains. This is RF amplifier. Match with this. Amplification application can be seen. You can have a voltage amplifier and a current amplifier, depending on R, C, L, the way you are going to use it. Resonance phenomena in the various domains. These TV receivers, there is a resonance which is playing. The radio, again, there's a resonance. The exact resonance is possible, then only you can pick up the signals. This is again beautiful things that you are able to hear because of this resonance guitar. This is again possible to see the that's phenomenon of resonance with respect to anything which is matching, then you can see the variation in the frequency, amplitudes. This is the swing again. When it's matching with the other frequencies, there's going to be a change in the amplitude. This is singer breaking the glass, you see, those pieces. What is that he has done? Okay. Now what is that he has done? Why it gets breaks into pieces?
He would be singing at a particular frequency.
Which is matching with the frequency, with the air columns is going to vibrate. No? Amplitude goes up, that with that bigger amplitude, this cannot withstand. See, there is a change in the amplitude, no? That goes beyond certain value, and it goes to pieces. Okay, that is what we are trying to do with this kind of an circuits. There is a bridge that has been collapsed because of the resonance. And this is again, okay, micro one using the resonance. Why study about these things and these components? Applications of resonance, which you have already seen some of them. You can see this is voltage amplifier, current amplifier. It can use as a filter. You see, it be used in the selecting the Disher stations and radios and TVs. You see how much is this applications are there. And this is in series. Exactly same thing happens. Okay, this is going to be a resonance point. The only thing, whether you are going to look at current or a voltage, depends on the way, the magnitude which you are interested. You can make either an RC, L in series, LCR in series or a parallel. So this is what you are. See, now you can impedance is coming here. The problem what we have done is inverse of that we are getting it. Okay, and plot them and see how the responses are and how they are able to connect them. Resonant point is same. And then you have a XL and XC, or what is what and how do they play a role in the circuit. With the frequencies, what is happening independently, each component can be plotted, capacities formed. You can see XL and XC separately. As I said, you can make them separately, all of them. All plots can be shown independently in a log scale. How do they respond with respect to the frequencies? Combinations, independent values, all the things which is understand how the phases are playing. You may ask, sir, why do you have a phase here? And this is the reason why you have a phase components here. Okay, and this is what the series LCR circuit parameters, current and voltages. Okay, and the phase component. And this is what the plots which is showing the detail. This is the phase. I think we are going to see the phase part also now. Okay, phase. This is what the result which we are going to look at it for the parallel RCR. This is what series gives. Two-factor. It's a very important one for electrical engineers. Another LCR circuit two factors here. Quality factor, which is connected in the form of other forms, other way with respect to the frequency, with respect to the capacitance. This magnitude can be evaluated. Voltages in series RLC circuits. So what happened to the across each one of them? What is the voltages? How do they respond? This is voltage across your elements at the resistance. Then you have a voltage across all the elements at resonance. What is happening? Voltages AC across all the elements. Now where is this? Variation DC. This is the peak, which is inductive component, voltage, capacitive component, resistive component. Probably this is going to be total component. That's what the result is given. Okay, and then bandwidth. All you are playing with this component parameter, what has been given for the given problem. Bandwidth and half power frequencies. Bandwidth of a half power frequency. And this is what your bandwidth of. Okay. This is what your angle in load during the bandwidth of frequencies in terms of the real and imaginary components. Bandwidth of half power frequencies in terms of all the other parameters. In terms of the L and RC, the component. Okay, this is what you have. Bandwidth of half power frequency, that's also has been calculated. And this all parameters you can evaluate, omega 1 and omega 2 and how they are connected, all of them and use it. And you can show picturely, all these things can be shown. And when I change the R and LC, this will be shifting. This can also be seen visually, one can feel it. Omega R can also be connected to the omega 1 omega bandwidth, through the bandwidth. See how these things are getting connected to each other. Omega 1 and omega 2 in terms of a resonance frequency with the Q factor, quality factor. So again, bandwidth and half hour frequencies with the various forms. Writing it to the left and right. So there are some conclusions. Yes, given voltage which appears across the reactive components can many times greater than that of the supply. Many times. The factor of magnification, voltage magnification in series circuit is called Q factor. These are very, very important. And RLC series circuit accepts maximum current from the source at resonance. For that reason, it's called an acceptor circuit. We have maximum current. Whereas in the other way around, if you make a parallel, then it's going to be a different way we are going to look at it. It's going to be a current will be minimum in that case. So this is the problem connected to is given R equal to 2, L equal to 1, C equal to this. Calculate all the parameters that has been described here. Understand this problem and work out all the parameters. And then there is another problem is given. 3 problems he has given, work out the results and complete the whole thing when it is parallel or series. Then go ahead with the parallel. Exactly same logic can be followed. Okay. The resonance point is same. Only the measurable quantity getting changed. When the current is maximum, this current is minimum in this case. This all you will understand when you start working out with the given circuits. This is You can see this, all of them are in parallel. Current magnification, bandwidth with other representations. Okay, practical parallel LSM circuits. See, this one C will be on the other side of it, then match it. Then repeat the whole thing. What is happening? That can also be studied. Ideal tank circuits. There are some conclusions. When you read the conclusion, you'll find there's going to be something interesting. You understand more. This is a rejector circuit and acceptor circuits. Then current voltage, you get changes. Q factor is connected to something else. It's different from what you have seen in the previous case. Okay, dynamic resistance, dynamic impedance or dynamic impedance. Okay, at present frequency. That's what we have already seen. And there's a table which gives for series and parallel circuits. Go through them. The problems are given. This is a fantastic problem to work it out with this Mathematica, and you can have a nice learning that is possible for you. Okay. Then select your own problem and go through the development. This is meant for electrical engineers also. And you know, physics is the base. The whole thing, physics is the base. So therefore, if you master your physical problem with this kind of an analysis, then your electrical engineering will be easy for this circuit analysis. And that already I shown that how much is the application. That is what you are trying to learn. I'll send this one. If you can take, somebody is really interested, all the problem, whatever it has been given, you can work it out through Mathematica and then have your own problems and understand what is that really happening when the RC is in parallel and series, and what the dynamics which is going on. Okay, that could be try to explore. I hope this will be useful for some of the people for an BSc third year students or first year or second year MSc. And what is needed for that has been already given to you through this Mathematica course. As I said, no, you can have the full width half maximum as a manipulative parameter. If I change this, the width variation can also be changed. That can be seen automatically. Okay, this variation, when I change the R, that also, because all parameters are get connected to this RLC, put them in a proper form here as a list plot. Like you see, I made a list plot for this dot. Generate them and then put it along with that. I change the parameters. You can see that these dot will be getting shifted. Full width half maximum dots will be moving out. If you make one such demo for students with this and other circuits, they can do it. Make it for LCR series and LCR parallel, they can do it. So that's how it should be learned. And what I refer to, this is what these dots which we have shown. Like this dots is possible here also. Full width half maximum, I can place it automatically here with the parameter. If I change this parameter, that shifting will also reflected here because that will be calculated automatically. Here it's calculated automatically for every point, every time. That's why you are getting it. So idea is what you have learned here, it will be useful here also. Mathematical code, what you are going to do. So like this, you can do it now. So hopefully we'll see the plot of this which we are seeing, and we'll try to see what is happening to this angle. Getting it now? You can see the 90 degree, which is, this is the point at which phase goes to 0, which means one particular frequency, the phase goes to 0, positive to negative. This is 90 degree here, plus, and 90 degree here, minus value, for the range of all the frequencies. You can see the shape of this curve can be modified. Okay? How it's getting affected by the variation R. This is with respect to C, and this is with respect to L. Okay, width consequences also can be seen. See, when I change this, it becomes sharper and sharper. Okay, one particular frequency it gets changes, isn't it? The phase goes to 0, one particular frequency. So that can be seen. It is clear here. It is bandwidth is little bigger here. If I take this resistance higher, then it goes down. It becomes sharper. The all can be visually seen. Okay. As I said, this is argument I have taken for plotting it. Okay, it takes automatically. If I put an argument of this, which means it evaluates every time sine component of this, cos component of that, takes the numbers for a sine of this, cos of this, and then arctan it finds, and that has been converted into angle by 180 degree divided by pi. This is the result that we have. Okay. Here again, I repeat, arctan, which I found by taking the imaginary divided by real, this expression. That expression has been put into this quantity. Okay. Arctan of this. They are one and the same. Okay. There's no difference between these two. Okay. These two are one and the same. You can always generate the maybe change the parameters. So now look at, they're one and the same. Correct now? They're perfect. Okay, when I have complex quantities, I want to solve. This is the complex quantity. Really complicated. I know that. Is it not? How do I locate this? By solving the equation. Well, it's easy to do that. Again, I will take the argument here. See? The arctan of this equation I have taken equal to 0, solve for omega. Equation as it is I have taken. Okay? Follow what I'm trying to do? This is what your phi angle. When I equal to 0, it is crossing from positive negative sign. At what frequency that happens very much depends on this L, R, and C. That is where the point it goes to 0. I solve for it. Solve that. I should get the same thing which whatever I tried or whatever I shown. This is the resonant point. 1 by square root of L into C. I'm able to get the result. Something fantastic now. You can solve this. And substitute the L and C value, you will get this point in the frequency domain. This is in the frequency scale. You can see this is the frequency scale. This point is nothing but 1.41. Where is it? Number 1.414. Okay, that number can be seen here also. So through pi also I can locate the resonant point. So which means most of the information is available here also, including real part, imaginary part, ABS value, all are available through this equation also. Through this also. Because you can see that this will be a ratio between these quantities. And if I find out independently, you would see that copy. I want to find out what is the real part and imaginary part separately. Take out this. Okay. Complex expense plus the back. This is real part separately. Then copy, paste over here. Find out what is the. So this is the real imaginary part. This is the real part. Inform. When you take the ratio, whatever is terms that are available that will be appearing in the form of this equation R by L omega minus R C R omega. This is the result that you would get automatically when you take the ratio and simplify. That's what the result I have used here separately instead of argument. Okay, so this is all about this problem, and you can try, as I said, I'm going to send that PDF file which contains so many problems for you to work out. You can try that and see that that something can be emerged, something extra learning that takes place for everyone else. Fine. Okay, is there any clarification required here? Somebody has any doubts? You can ask now for a minute. That's all. Anything you wanted to have? So no doubts here. Everything is understandable now. We'll go to the next problem, which is rather easy. I think I have given it, making some error in that, and then I have given the problem. Now you can see this is. I do not know whether I can. This problem is it's here. 3.1. An object moves in one dimension according to this x of t equal to 5t e per minute t square. Find the velocity and acceleration and plot these along with the position on a single graph with the legends, not the legends. Okay. Find the time at which there is no net force on the object. Okay. So I have given this. Probably I made some mistake here. When you find out what is the error in this, What is the error? In this some error is here. No error. Find out that. Just come within a minute.
Sir, your mic is muted.
Yeah. So the error is the 5 which I missed here. Am I right?
Sir, I didn't
See,
understand why.
when I sent this exercise, I given this clue also. Okay, how to do this. But when I entered it, I purposely removed this 5 and I gave and correct the problem and work it out. This I have given like this. You can refer your exercise. This is what I have given. And then I solved it. And this solution gives, because acceleration is known to me, that's nothing but your force. Am I right? This equation is displacement. First derivative, second derivative gives the acceleration. Multiply with the mass. Okay, that's going to be force. But the m into a doesn't matter when you solve the at a point where the net force goes to 0. So I just solved the acceleration itself. I did it now here with this and found the solution. I said there is a mistake in this problem which I have given to you when I give this result. I missed this 5. I removed that purposely so that when you are working out this problem, you are careful about seeing this expression properly. Substitution should be done properly. Now I am going to correct that by putting 5 times t into e power minus. That is what the problem. But what I have given is the solution in this form. So there is an error. I used to ask to correct it, write down neatly about all the possible steps that is required. So 5, and this time derivative twice I am doing it. Okay. T is taken twice. Derivative once is velocity, second time is the acceleration. He is asked to find out position. What is that? Velocity and acceleration. I found this as an acceleration. If you wanted to have the velocity, you do it, define it as v here and make this is 1. This is velocity. This is your acceleration. This is what I would expect from the people when you work out the problem. Okay. Now the question is find the time at which there is no net force on the object. What does it mean? This acceleration must be equal to 0. Equal to 0. Solve them. And you find the time at which it goes to 0, which I can find out. Okay. This time at which it goes to 0. And is that really true? It's possible for us to find out by plot the B and A. And you can find out that So let me make a plot of B and A, put it in the list here. This is a simple plot. It's not a great or how. Variable is T. How long you can go? Somewhere between 0 to 5 seconds is enough for us, or just check whether it's close to 0. Yeah, it's possible. Only this plot range all. Then you can see where it goes to 0. And what is what? How do I know? I don't know what is this one. What is this curve? So what do? I make a plot tile, simplest thing. I'll make it as one other is red one, other one is blue, so that I know what is what. First one is going to be the red one, which is going to be velocity. And this blue is this one. Say velocity becomes at this point slope equal to 0, acceleration must be crossing here. You can see slope equal to 0. Slope of this curve is acceleration. That goes to 0 at this point. 1 point some 2 seconds or so. That is what the problem. They asked to find out net force at this point goes to 0. It's also equal to that the slope of the velocity curve goes to 0. Because this slope is this curve. Is that clear for all of you? These are the things you should attempt to understand. Is it clear for all of you?
Yes, sir.
Fantastic problem, huh? You can see how nicely one can understand about the acceleration velocity. And if you want, you can plot this x of t also. It's not the same curve you put it, and you connect the displacement and velocity again. You know what I'm referring? Plot x of t also, then connect the displacement and velocity, then velocity and acceleration. Find out how they are interrelated. Okay, you do it yourself and try to get an understanding. Now you try to do this problem also. It is very simple. X of t is given. Now show that this from here you can get this one. F of t from f of t, I can get this relation. That is what this problem says. Okay, I am not getting this. I made a mistake here. Then any mistake is done? Yes. Half should be added here. If I add half here, is the mass by 2 and solve. I have a result what is given in this problem. Over. Done. It is a simple second order force equation. Solve for x of t. Take the first result, and this is same as what has been given here. Interrelation, I should know how they are getting connected. That's very, very important for you. If you have that, how this physics is pulled out through the differentiation and integrations. It's being pulled out through the differentiation and integration in terms of the displacement, velocity, and acceleration. That's what your dynamics is. Okay, I'll stop here. If you have any questions, we can have some questions. We'll be happy to answer. Please think about the problems as much as possible. Physically, you think, computationally, you think. Then look into these problems and show that you have an enormous understanding that it will be possible. It's so clear by looking at these problems. Okay? Yeah.
Sir, I asked if two equations simultaneously solving and
two different equations, in fact. For example, I have a say parabola is there, or a hyperbola is there. There is a line passing through that.
Yes.
It can be solved. Same solve. Put the both equations.
Okay.
Right. See, it is not a difficult thing. That's what I want to say here. Put the equation for a parabola. Okay. Put the equation for the straight line. Right. Plot them on it. They are going to meet each other. Okay. Meeting each other means I have to equate them.
Yes, sir.
Solve. I'll get both the crossing both the parabolic, both the points, or it is crossing a straight line. I'll get two rules. I'll show you in the next class nicely.
Sir, yes, sir.
There are very many things like that we have. I'll show you some of the things which is very required. In fact, so far which you have learned also, it's all interconnected and we have shown it. I'll show you through this mathematics also. There are many things which are interlinked. That interlink can be shown. Okay. Pictorial form, analytical equation form, and then number form also. Okay.
Yes, sir.
We'll do that. I'll show you some interesting problems. Yes. Quite interesting to understand.
So tomorrow's class is at
Tomorrow, yes, we can have it by what time? 2:30?
2:30.
Okay.
What about the participants? You prefer this time or?
Participant means?
I'm asking whether your choice is in the afternoon or morning.
You can ask choice from them.
Okay.
I think afternoon would be also better, no problem. Or morning
yes,
also.
sir.
I don't have any problem. Okay?
Yes, sir. Then 2:30 would be okay then.
2:30 would be okay.
Students are not telling about their choice.
Okay. 2:30, fine. Okay, we'll meet 2:30.